Welcome to homework set number 8 for ECE 461 control systems. This homework set looks at root locus plots, sketching the root locus with complex poles and zeros, gain compensation, and lead compensation. So the first problem is, given a system with complex poles, sketch the root locus. So here's what it looks like. The open loop poles and zeros are right here. So here's a pole, zero, pole, and pole. The real axis loci are even odd. Here's the even number of poles and zeros, odd, even. So there's the real axis loci. There is no breakaway point. The pole goes to 0. There are 3 poles, 1 0 gives you 2 extra poles. That gives you 2 asymptotes. So 2 times theta is 180. Solve for theta, I get plus minus 90 degrees. So here's the asymptote. And the center mass is the asymptote intersect. So this one's at 0, minus 1, minus 1. And zeros act out like a negative mass. They're opposite poles. So this is a plus 1 mass at minus 5. The average of them is plus 1.5. So here's the asymptote, plus minus 90 degrees at plus 1.5. The departure angle, this guy right here, the angles have to add up to 180 degrees as I approach the pole. Well, any point of the root locus angles that up to 180. So evaluate everything except this pole at minus 1 plus J2. All this adds together to, so where is it? Adds up to 180 degrees. So 180 degrees plus this angle equals 180. That turns out to be 0 degrees. So I leave this pole at 0 degrees and approach the asymptote. That's the root locus. Complex zeros are similar. So here I've got 4 poles, 2 zeros. Real axis loci, poles come together. So there's even, odd, even, odd, even. When there's an odd number of poles and zeros to the right, I'm on the real axis loci. Breakaway point is right in the middle, pushed right by these minus charges. Poles act as minus charges, zeros plus charges. So it's the midpoint, pushed right, midpoint, pushed left. Asymptotes. I've got 4 poles, 2 zeros, gives you 2 extra asymptotes. So we get 2 times theta is 180. Again, the angle is plus minus 90 degrees. And the asymptote intersect is the center of mass. So the intercept is the average of minus 6, minus 4, minus 2, and 0, minus zeros, minus 1, minus 1, divided by 2, gives an asymptote intersect of minus 5. So there's my asymptote. I split apart at the breakaway point and then approach the asymptote. The approach angle is angles have to add up to 180. Analyze everything except this angle. It's got to add up to 180. Everything except that pole is minus 145 degrees. So this must contribute an extra minus 35 degrees. So I approach the 0 at an angle of minus 35 degrees. Problem 3 is gain compensation. Here is a 4th order system. That's the 4th order model for a 10-stage RC filter. Design a gain compensator that results in the passive system with no overshoot per step response. The approach there is to sketch the root locus plot. So here's your pole, 2 dominant poles, and there's 2 other poles over here. Take the dominant pole in the root locus. Here's the root locus. I can get any response that's on the root locus. The point that I'm shooting for is right here. As I crank up K, I get a faster and faster system. Go beyond this point and get overshoot. So the highest gain with no overshoot is at the breakaway point. Once I know the point, at any point on the root locus, G times K is minus 1. Solve for K, and I get K is 1.34. With that, I can form the closed loop system, GK over 1 plus GK. I pick K to put a dominant pole at minus 1.65, and sure enough, there's a pole where I put it. There's 3 other poles because this is a 4th order system. This is almost at the breakaway point. I'm a little bit off, which is why they don't exactly match, but close. The settling time. For over the real part of the dominant pole is roughly the settling time. It's about 2.42 seconds. The error constant is the DC gain. Evaluate g of s at s equals 0, and kp is g of s times k. kp is 0.95. So the error per step input is 1 over kp plus 1, 0.51. Plotting the step response. 1 is up here. Here's the steady state error per step input. And here's the DC gain. Okay, with no overshoot. 4-second settling time, behaving about like I expect. Problem 4 is now designed for 20% overshoot. So here I sketch the root locus, freeze it, draw the damping line. I draw this line, plot that on the root locus plot. I'm going to go origin, 0, 0 is 1 point, minus 3, the tangent of the angle, times 3. 2 points determines the line. There's my zeta line. Where it intersects my root locus plot is my design point. So from the graph, it looks like S is roughly minus 1.2 plus J 2.36. Analyzing G of S at that point gives me a negative real number that tells me this point is on the root locus. The angle is 180 degrees. To find K, K is whatever it takes to make the gain 1 at that frequency. K is 6. So if I try it, close the feedback loop when K is 6, here's my dominant pole, this complex conjugate, and 2 other poles. The settling time is for over the real part of the dominant pole. Steady state error is 1 over kp plus 1. Kp is the gain of g of s times k as s goes to 0. Plot the step response, and I've got better tracking. There's the error per step input. Here's my 20% overshoot. Problem 5 is design a lead compensator that gives me 20% overshoot. So there's kind of 2 camps on this. I either cancel the slowest pole or the next slowest one. You actually want to cancel the next slowest one. This is the pole closest to the origin. That keeps the steady state error small. It's as close as I can get to an integrator as I can for this problem. So keep the slowest pole. Cancel the next slowest one. Move it 10 times further out. So here's g times k. Sketch the new improved root locus. Find the point where the new improved root locus hits your damping line. At that point, make the gain 1. So here's S. Any point on the root locus, g times k is minus 1. Negative real says that point's on the root locus. Pick k to make the gain 1. Here's k. So the closed loop system is now gk over 1 plus gk. The dominant pole is where I put it, plus its complex conjugate, plus 2 others. Settling time is 4 over the real part of the pole. Error constant is the DC gain. Error per step input is 1 over kp plus 1. Better tracking. So here's the step response of the lead compensator system. So lead compensators kind of do everything. They reduce the steady state error, give you a faster system, this overall better system. The last part is give me an op-amp circuit to implement it. Here's K of S. What I like doing is, I'll guess this is 1 meg. I've got 4 degrees of freedom, 3 constraints, meaning something's arbitrary. Let's make this 1 meg. As S goes to infinity, this is a short. S goes to infinity, the gain is 126. So 1 meg over 126 gives you 7.9 K. At DC, capacitors don't matter at DC. At DC, I want the gain of 12.6. Gives you the total of 80K. This is 7.9K. Here's the remainder, 71K. Then define C. That's the 0. So I switch from S, from 3.4 to S at S equals 3.4. I switch from resistive to capacitive at 1 over RC is 3.4. I know R, solve for C. C is 4.1 microfarads. Here's the circuit to implement my lead compensator. And with it, that is homework set number 8 for ECE 461.